right, welcome. So, anyone that did not pick up your exams from last time, you can come get them after class. They are up here. Any questions from last week? Any questions? So, back to lecture 8. So last week we talked about first order solutions. Well, first we talked about capacitors, inductors, how they act in DC situations, meaning they've sat there for a long time, and then how to use them to solve circuits for just one capacitor or one inductor in the circuit. So this was a first order, meaning there was just one differential in there from that capacitor or inductor. And then getting that general form solution, knowing what the form was beforehand, and then finding the values to put into that general form solution. We also talked about the time constant. So any questions about those concepts so far? Okay. All right, so a poll today, well actually before we move on, quiz for today is SINE. It's all lowercase, SINE. So that will be what you will need for access for it, SINE. So again, you can start that and do it while we're going through the material, or you can do it after. It will be due by tomorrow night. All right, a poll. As far as missing the ability to be in person lecturing, do you prefer the way it was last Friday, where it was a shorter, tried to make it pretty short, like review or content video, and then I gave separately the videos for the solutions for the problems? Yeah. So that would be A. B is to do a remote lecture where I wouldn't physically be here, but we would all meet on Zoom and do a lecture that way, or a TA lecture, or a combination where we would meet, I would have the pre-recorded with the example videos, and then we would meet at our normal time remotely for maybe a shorter question and answer kind of period. So with that, oh, I forgot to put the QR version for this one. So take a second if you would answer anonymously your preference. And also put in there any other comments. Interesting. A's and B's. So I guess A was, it went pretty well from last Friday. Seeing some yeses, that was a good way of doing the missing time. Okay. Got a lot of preference for the A. Okay. So B doing the remote lecture, and D and A all sound kind of similar. So I will let you know. I have a situation, so I'll let you know what ends up happening. So for Wednesday, let's plan for sure. It will be recorded again, so there'll not be a in-person meeting on Wednesday. We'll just do the recording and example videos, and then I will let you know if I need to still miss. We'll decide on Friday and see what that one will be. So for now, don't plan on class this Wednesday in person. Again, it will be recorded lecture with the example lectures, and then you'll have to take the attendance quiz to verify you did watch it and understood some of it. Does that sound good? Seeing some yeses. Okay. All right, great. Thank you. Thank you everyone for participating in that. Okay. So Today's topic is going to be the last topics before your next exam. So next exam will be November 12th. Put it on here. So exam 2, it will be on Wednesday, November 12th. Exam 2 will be Wednesday, November 12th. And it will cover the first order, so capacitors, inductors, and first order solution and all the concepts related to that. Sinusoidal signals, which we'll go over today, and I'll explain what I expect from that one. And then complex numbers and phasor concept. So that will be the content of this second exam. This covers chapter 5 and then so it's chapter 5, and then chapter 7 is 7-1 to 7-3. So those will be the chapter contents of that. So the goals of today is to be able to express a sine wave in the time or sinusoidal wave in the time and frequency. Frequency is called, what is going to become more familiar to you in electrical engineering, we call it the phasor domain or frequency domain. And so phasor is slightly different than just frequency, but I'll kind of get into that in a minute. But basically converting between the two is very important. I'm going to explain what phase lag and lead means and how to calculate it. And then in the frequency domain, how do you convert between rectangular and polar forms? So this is where the complex numbers comes in. Some of you may not have seen complex numbers for years. When I pulled another student, they were like, I didn't see that since middle school. So if complex numbers is rusty for you, make sure you do go and review. There's some links to review the complex numbers. Khan Academy is great for complex number reviewing, how to look at the plane and be able to calculate them right away. We are going to use those very frequently, and so you need to know how to subtract, multiply, and divide. And so I'm going to show you an easier way to do that than just time domain, where it's sinusoid plus sinusoid plus sinusoid plus sinusoid. There's a much easier way. So we're going to learn the easier way to do that. But in order to do that, you need to be really good at complex numbers, or understand your calculator well enough to make sure to use your calculator to be able to do it. So sinusoidal signals to start with. So what is a sinusoidal signal? Anybody have, how would you describe a sinusoid? Go for it.
Just AC, basically?
Basically an AC. So we have looked at DC already, meaning that DC we look at like a battery, voltage constant. AC is alternating, so something that alternates with respect to time. So it changes over time. We have the characteristics of it is amplitude, and amplitude is going to be the top and the bottom of the sinusoid when it's centered around 0. When I say centered around 0 is on an oscilloscope. When you measure these signals in a lab setting, it may shift up and it may shift down on the screen. What causes that shift is going to be a battery or constant voltage in your system. So you would have both a constant DC value, and then the AC is what is alternating around the constant. So this may not be an actual 0. This may be, I'll call it Vx, and then this would be Vx plus Vm, and this would be Vx minus Vm. So this value would be the DC value. And the nice thing about signals is that you can have a DC value and an AC. You can separate them out and then analyze it like superposition, where you analyze just DC without any AC content, and then remove the DC, analyze the AC and just that content, and then add them together for your total. So that was why it was important for us to understand the concept of superposition kind of before we move into this little bit more complicated system. So the amplitude here, you would say it is VM. And what if this started out, let me draw it down here, at, oh, I don't want blue, at a, not getting a different color, there we go. If we started out at a negative VM instead of a positive VM, your amplitude would be a minus. All right, the other characteristic is phase, and then a period. So, oh wait, this is not written. Phase, we use theta, and for period is going to be T. So amplitude is how high the voltage or how low the voltage goes around a center point. And so you need to, if it's shifted, you have to figure out what is that center point value. That will be your DC component of it. And then you need to find out the shift of the VM and the minus VM. Okay, so I'm going to come back to the phase, and then the period is going to be where you've gone through one cycle. So this goes down, and then it goes back up, and then it repeats. So this distance is what we call your time period, from where it's either measuring from peak to peak or where it crosses zero to where it crosses zero again. So this would be another way to determine where your time period T is. You can draw straight lines. Okay. So with a period, if you find your period, you can find frequency. Frequency will be in hertz, is your units, which is 1/seconds. And then you find this by taking 1 over your period, where your period is in seconds. To get to angular frequency, omega is going to be the variable for it. It is going to be radians per second. And to convert from frequency to radians per second, it's 2 pi f. So this is memorize, and then understand what the time period is. All right, so phase is easier to understand phase when you're comparing it to something else. So a phase is where you don't have any change. So this would be the blue line in the middle is when you have no phase shift. When you have a shift, either to the right or the left, you can see how instead of being right at the peak at 0, your peak is either shifted to the right or shifted to the left. In time, if you're to look at this, what you do on an oscilloscope typically is you're going to capture your window of your sinusoids. you're going to mark what is the input, and that's what you're going to put at time 0. And then you're going to compare everything to your input signal. So these would be output signals, or you're measuring a voltage across of an element or a current in the element, depending on what you're trying to get current or voltage out of there. So comparing it to your input signal is going to be, there's not going to be a shift on the first one unless you're told that there's a shift. And then if it is on the oscilloscope and it actually is to the right of it, this is called, it's lagging. And then this one would be leading. So this has the three, this is showing the 3 different, no shift, and then if you have a plus pi over 4, or if you have a minus pi over 4. Anyone remember how to convert from, so this is going to be in radians when you see pi in it. How do we convert from radians to degrees? Anybody remember? Okay. So we know that 180 degrees equals pi. So hopefully this looks familiar. So 0, pi halves, pi, and either negative pi halves, or you can do, oh, sorry, down there. Or, what is it, 3? Thank you, 3 pi halves. Pi 2, 3, there we go, yeah. Or 3 pi halves. Okay, and then using the conversion, so you use this as your conversion of 180 degrees is equal to pi. So if you're converting, you would use 180 degrees over pi times something like pi force gives me 45 degrees. So this would be how you would convert that pi force to degrees. This is going to be 90 degrees, 180 degrees, 270, or a minus 90. So this is that circle that hopefully looks a little bit similar. Do you guys remember this? Middle school, maybe, way back when. Okay, refreshing your memory. Okay, so when we talk about leading or lagging signal, this is meaning that that input signal is what we're referencing to. And in comparison to that, we're either leading with a current, or we're lagging in a current, or we're leading in a voltage or lagging in a voltage. So how do we actually measure and find what this is as far as that value of pi force, or 45 degrees? So given a, so here it is marked. So here I see, like, well, I'm going to pick a point on the 0 that's easy to measure against. So I'm going to pick this point of the green graph and then look at where it cycles through and crosses 0 again. And it looks like it does that here at 0.0005 seconds. So then I count how many cycles are between there. So I go down and up, that's 1 cycle. Down and up again, that would be 2 cycles that are happening between those periods of time. So on an oscilloscope, this is what I would do, is I would get matched up as close as I can to see, like, oh, where can I measure this? A lot of times you can just capture it and just even put your cursor on it, and it will show you what those measurements are. If you've captured it and you're like outside the software, then you have to kind of do it extrapolating like this. So I know here the first thing to find is my time period. So I said I had 0.0005, 2 cycles of that. So that gives me 2.5 times 10 to the minus fourth, which then I know my frequency is going to be 1 over that, and that gives me 4,000 hertz. So my angle is actually going to be omega times the change in time. So in this case, the frequency is 4,000, sorry, I missed the hertz point of that. And then I need to measure the delta t time difference between these two. So I measured using the oscilloscope the black point in comparison to the green and in comparison to the red. And so that gave me these 3 cursor points. So my delta t is going to be the differences between the green, which is the middle, and then the other 2. So using that, 0, 1, 2, 3, 4. 1, 2, 3, 4. So 9375 minus 0.1234625. So this gives me 3.125 times 10 to the minus 5, and then taking 0.0000625, sorry, 4 zeros, minus 0.1234312, I get 3.122 times 10 to the minus 5th. So theta now is going to be 2 pi times 4,000, and then I can calculate each of these and then either take the average or, sorry, each of these is different ones, so this is theta 1 and this will be theta 2. So is this going to be a theta in radians or in degrees? It will be in radians because I have the pi in there. So this was 3.125. So 0.7854 radians. And this one is 0.7846 radians. So if I want these in degrees, I just take 180 times pi times their value. And so this is 44.9, so approximately 45 degrees, and again this is going to be approximately 45 degrees. So that is how I could calculate that theta just from the graph itself. All right, questions on this? You guys following all these? Okay, so on the unit practice, there's more of these that you can do for unit practice ones. and I'll do an example for Wednesday. So try it on your own. For the example videos, again, try and do it yourself, and then look at either the notes for the answers to see, did I do it right, or look at the video solution. Yes?
So we're always trying to convert from radians to degrees to our final data.
I like degrees because I know what that means to me. Radians just doesn't register in my mind as much, where I'm like, oh, I know where exactly your 45 degrees is. So that's more my preference. So it's kind of your own preference, or what the problem asks for.
So is the purple the delta T and then the phase shift?
Sorry, say that louder.
Is the purple the delta T?
Yeah.
And then the phase shift is blue?
Yeah, so these are the delta T's. And then I put that delta T into the equation.
Should we want to have the values be negative since we're shifting either left or right?
Oh, yes, so thank you. So to determine if it's positive or negative, so here to write these, thank you for doing that. We're gonna say the green one has no shift. So I'm gonna call this V1, and this one V2, and this one V3. So if I wanna write the mathematical expression for this, what is my amplitude for this one? Can you read it? 4. So I put 4. And is it cosine or sine when it passes through 0? Which one? Sine. Okay. Sine. And then what was, we can either do 4,000 hertz, or you need to do 2 pi 4,000. So the default is going to be in omega, and that will become important in a minute. So we would do it as 2 pi f, or we have to specify that it's in hertz, and then that will be time. So that one has no shift, so that would be our signal for that one. For 2, again, it's going to be 4 sine, I'll just do 8,000 pi t. And then because it's to the left, it's going to be a plus because it's leading pi force. Or we could say 45, and again, you need to make sure the degrees is noted there. So default in theta is going to be radians. Yes.
Would it be negative sign as it goes down after 0?
You mean a negative amplitude, or what do you mean by negative?
Like you said 4 sine. Would it be negative 4 sine?
So the amplitude is negative if the, oh, it does go down, doesn't it? Yeah, you're right. Sorry, yes, negative 4, thank you. It's actually going to be negative because it does go down. Sine, which should be going up. And then red. So V3 is going to be a negative 4 sine 8,000 t plus, or I mean minus 5 force. Pretty sure I did this. Yeah, okay. Thank you. So, yes, it should be negative sign. Or negative 4. All right, questions about this, about writing the mathematical expressions. Okay. So where are you going to be getting these mathematical expressions? It's from the oscilloscopes. So when you're measuring things in the lab, you're going to want to describe them mathematically to do simulations or to modify designs, so on. So you're going to want to know how to write these. So takeaway from this is being able to write these mathematically. So determining what the frequency is, what the amplitude is, and what the phase shift is. Okay? And that phase shift will always be relative to an input signal. So why do we want to look at sinusoids? Because every single application that you can think of has a sinusoid in it. So power in your house actually is sinusoidal. So it comes out of the wall with an AC signal. And then your electronics and your power blocks that you plug into the wall actually convert it from that AC signal into a DC signal. So if you look on those that have a power cord with you, you can look on the back of it and there will be ratings on it. So it will show you what your DC value is and it will show you what your current limitations are on them. All right, radio waves, microwaves, light waves, radar, mobile cell service, Bluetooth, all of these are sinusoids that carry information, and then a receiver will then interpret that information from the sinusoid. So digital systems, how do digital systems fit in? Do they have a sinusoid signal in them? They actually do. So it's converted, so everything in the real world is a sinusoid. So we model everything as a sinusoid, and then we convert it into a digital number, and the digital number will correspond to a voltage. And then it's then interpreted digitally and manipulated, analyzed, whatever, digitally. So everything actually has a sinusoidal system. Power, if you're interested in it, ECE 3600 is kind of the next class to be able to kind of get into more information about power. And then as I said, like information can be carried on signals. So when you're looking at gamma rays, X-rays, UV, infrared, radar, TV and radio, so depending on the wavelengths of each of these, you look at the electromagnetic side of it. So when you're transmitting and receiving, those are antennas, that falls under electromagnetics. So electromagnetics course is ECE 3300. So you want to make sure you have, most of you here probably have the math, but you want to make sure you have enough math content to be able to then move, because you look at electric fields, which is in Calculus 3. So those that are either in Math 3140 or Calculus 3, that material is actually applicable in 3300, and she describes it in such, well, I guess it's him and her. Whoever's teaching it describes it in a way that, again, you're gonna learn how to make use of it in an easier way than you probably learned in math, and how to interpret a lot of the information to actually make applications, which is, I think it's really fun. So every single signal, which is very interesting, even when it looks chaotic such as this, can be modeled by a summation of a whole bunch of sinusoids. This summation is actually called Fourier series. Where you can use a whole bunch of sinusoids and then you be able to show how much impact they actually have to this expression. So one might have a really large magnitude, which means it's the majority of the signal is that one. And really cool tools now that you can actually feed this into something in MATLAB, and it will actually give you the whole Fourier series for you, so you don't have to like come up with how do I describe it. So there are tools out there that you can actually feed the signal in, and then it will show you the mathematical expression of all of these summations and how much contribution from each one. On power lines, you get, if you ever look at a power line, it looks like this, where it looks like, oh, there's a lot of noise and chaos kind of going on. Depending on what loads you put on that line and that distribution line of power, you will get this, and then again, you feed that into a tool and it can give you this mathematical expression. So we want to know, like, okay, great, that kind of can be automated for us. So learning more about these varying signals and the summation of them as sinusoids is in math, as I said, 3140 or 3150, and then 3500, you can learn more about that part of it. These were just some examples. All right, this next sheet we'll kind of come back to, but it is a nice, useful reference sheet to remember a lot of the relationships. And then this is the coordination systems from rectangular to polar, and we'll go into that again in more detail. And then all of the identities that are very useful. One really, I actually graphed these so that you can see that sine is actually equal to cosine of x minus 90. So this is going to be an important conversion because we always, by default, just like we have conventional current, you're going to want to describe everything in cosine form. So we're going to change those signs into cosine forms. So going from sine to cosine, if you know that first one we were like, oh, it's easier to write it as a sine function, then we can just add a minus 90, and then we had minus sign, so we'll actually do a plus 90. So just remembering these two. And I forget, so you can also go graph them to remember which one is plus and which one is minus. Okay, so let's change this. This was what we had above on the graph. This is the minus 45 degree one. So want to change it first to cosine form and then determine the amplitude, frequency, period, and phase angle. So take a second to find those values. All right, so changing this, you just add a plus 90 to change from minus sign to cosine. And so you just add those angles together, so plus 45 degrees. Your amplitude is then 4. Your frequency is 8,000 pi. And what will these units be?
Hertz.
It will be radians per second. Why did you think hertz? Yep, so remember, if it's not stated as hertz in there, it's going to be default of radians per second. Okay, so it would have to be 4,000 hertz T to have it in hertz. So the default unit is what you always go to if you don't have an actual specification. So as you can see in the degrees, or in the theta, it has degrees listed there still. So the default, if it wasn't listed there, would be to assume it's in radians. Okay, questions on these? On this? You guys good? Easy? Hopefully? Straightforward? Okay, great. All right. All right, so the next step is to think about when we have a circuit. We've only, again, looked at one inductor, one capacitor. Now if we have multiple ones, I had said before, each one of those contributes a differential. So if I have 5, say I have 3 capacitors, 2 inductors, I have 5 time-dependent elements, that's going to be a 5th order differential equation. Anybody want to solve that by hand? I hope not. I do not want to. So what we do, and this is the trick, is that we go from the time domain, which is our t, I'll do it as like, okay, so this is an abstract concept, is that we move from the time domain into what we call this frequency domain. So in the time domain, we have differentials. We also have integration. Oops, can integrate. An integration. So in the frequency domain, well, let me go. And so in the time domain, going back to this, we get the expressions that we just derived. So we get, 4 cosine 8,000 pi t plus 45 degrees. So with this is of the form, this is omega t. We have a cosine omega t plus phi. And what we do is we transform it and we go from time domain, and now we're going to transform all of our elements in the circuit into a frequency domain. That transformation, once we transform the signal, we call it a phasor when it's a phasor. I'll say it'll be easier. So the expression is called the phasor. So in the time domain, we're used to that mathematical expression as a cosine sine. In the frequency domain, we are going to use that term as a phasor. And why we do this is so that now, instead of a differential and an integration, there's such a neat trick that it just becomes that we can add, subtract, multiply, and divide. And in the time domain, that represents what's happening with a differentiation and an integration. Way easier to add, subtract, multiply, and divide numbers, right? Than differentiating, integrating. So this is where this is a really powerful trick to do. So way easier to manipulate. And we can get the same results. We can get voltage, we can get current. They're just going to be in a complex form. So they're either going to be in the two types of complex forms. A phasor refers to the polar form. The rectangular form it usually describes impedance. And impedance and resistance kind of mean the same thing. So when impedance is said, that just means basically what we've already known as a resistance. We use the word impedance though because now it might be a complex number instead of just one resistance value. So once we get a variable answer that we like, solve for variable. So for wanted variable, maybe I'll do V or I. We do an inverse transform. And we get back to the time domain. It's a really cool method, makes way easier to calculate. We just have to work with complex numbers. So that's what we're going to practice next, is being able to convert from the time domain into the frequency domain, being able to add, subtract, multiply, and divide complex numbers. So the frequency domain is a little bit hard to abstractly grasp your head on. When we're talking about this, we're talking about the actual plane where you have a imaginary axis and a real axis. So on this imaginary and real plane, which is the frequency domain, you are going to have a vector magnitude and a vector angle. So your polar form of this will look like the magnitude A, E raised to the J theta. And for the rectangular form of this, green, you're going to have an X part on the real and a Y part on the imaginary. And so your rectangular form is X plus Y, and then we use J for our imaginary number. Where in the past you've probably all used I. What looks confusing about using I for us? Because we use I for current. So because we use I for current, we use J instead for imaginary. Otherwise, it gets to be a little bit confusing, like what are you talking about with all these I's? So we use J instead of that I. And the only reason is to not lead to confusion. All right. Conversions. So for rectangular form, if I have A1 plus B1J, A2 plus B2J, and I want to add those together, I simply will add the real portions and add the imaginary portions. Way easier, right? Yes.
For the polar, is that the Greek letter phi?
Sorry, what? Is it?
For the polar absolute A, e to the J, is that the Greek letter phi?
Oh, sorry. That's theta. And theta always comes from 0 to the angle. Phi, sorry. It is phi. I said theta, didn't I? Yeah, sorry. I theta. I tend to do theta and phi the same. Okay. To me, they're kind of the same. Sorry, it is. I did draw phi and phi instead of theta. Sorry about that. Yes, they're interchangeable for me. They're meaning an angle, but thank you for clarifying to make sure that is more clear. All right, so if I subtract these, I would just, again, subtract the real portions and then subtract the imaginary. Way easier to do than multiplying or dividing, adding a sinusoid with another sinusoid with another sinusoid with another sinusoid. So add, subtract are going to be way easier in rectangular form. Multiplying is a lot harder in rectangular form, so we usually convert it into polar first. And then the nice thing about polar, say we have A1 E J phi 1, A2 E J simplify too is that you just divide the magnitudes, and then the exponential property makes this really nice that you can bring the exponents of the exponential. If it's a division, it's a negative. If it's a multiplication, it's add. So with this one, you just multiply, sorry, this is 3. And then you're going to add the angles. So that makes it really nice. So summary polar is usually multiplication, division is usually easiest form to do, and in rectangular it's subtraction and addition. So one last thing on these. So in the frequency domain, the other thing that you need to understand is what we call quadrants. So sometimes the quadrants will actually, the calculators will actually give you the wrong quadrant. And that's because if you have going back to the conversions, so to convert between the different forms of rectangular and polar, if you have the polar, which is expressed as the magnitude of z, and in this one it's theta, even though I wrote phi, so you're going to take x in the rectangular form from polar, so going from polar to rectangular, your x value is going to be the magnitude times cosine theta, and then y is going to be magnitude sine theta. And then going the other way, from rectangular to polar, your magnitude is going to be your x squared plus y squared square root of it, and your theta is going to be the inverse tangent of that imaginary component, which is the y, over the real component of x. So if you have a negative y and a negative real, so y and x are negatives, you're going to get a positive theta, which looks like it's in the wrong quadrant. So this is why you have to understand what your values are before you convert them. And as I said, calculators will give you a lot of time a different one. So if I have a negative, so remember this is your y is imaginary and your x is real. So if I have a negative x and a negative y, that is going to put me at this quadrant 3. But the calculator will show it will think you're in quadrant 1. So you need to know where you are. That makes a difference for us because I'll show you in the next unit how you convert the inductor and the capacitance, but it will change what component you have when you interpret it. So if you have a capacitor, it actually gives you a negative imaginary number, and when you have an inductor, it gives you a positive. So if you have that sign wrong, you're going to use the wrong component. So that's not a good thing. So that's why it's important for us to understand also what quadrant are we in. So we had, where is plus 45 degrees going to be? Quadrant 1. Where's negative 45 degrees going to be?
4.
Quadrant 4. So these are really easy if you only have one that's negative and the other one's positive. The harder ones are quadrants 2 and 3, because if you have a negative negative your value will actually come out positive from a calculator. And if you have a negative x and a positive imaginary, it may look like it's in quadrant 4, but it's actually in quadrant 2. So if you get, let's see, 90, 100 degrees, where are you? 2. And if I get 200 degrees, you'd be in 3. Okay. So just understand those quadrants. Again, these are questions that are on that unit practice too. All right, so gone over that, gone over those. Anybody have the quiz up that I haven't answered any of the questions on there yet? Feel free to ask. Yes.
Euler's something.
Oh, thank you. Yes. Okay. Yeah, so Euler's identity. So Euler's identity, I'm not going to lose my battery. So this is what Euler's identity is. It's the conversion between the j theta and cosine theta plus j sine theta. So this allows us to do all of these conversions. Anybody have that question up? I can't remember what it asked for Euler's.
This is what is true about it. It's using Phasor analysis to simplify signal transformations, but its exponential trig functions is not useful. Finds imaginary J.
Okay. So basically it is all of what we've talked about as far as it is what is used to be able to convert into the rectangular and polar coordinates. So all of those that you went through as far as it is going to be helpful to reduce our analysis, because then we're in the polar or rectangular form and we can manipulate all of those expressions. Was there any more questions on that one, or were you able to answer the rest? Okay. Any other questions that I haven't addressed that anybody who has the quiz up? Okay. Let's see. Make sure I do. Quadrant 3. Okay. This will be. All right, so those phasors is, again, just meaning that we're in which form when we say specifically phasor? Polar or rectangular? Polar, good. Okay. So remember that phasor refers to polar form specifically. So when we have a signal like we had before, the way to transform it from one domain to the other is with the omega. So the omega will stay the same. What will change in your circuit is the shift, depending on what elements you have in there. So you don't change the actual frequency, you're going to just change the shift from the components that are in there. So in the phasor domain, all we look at is the actual magnitude, and then if we have a shift. So when we convert these, as I said, we have to transform them. And there are two ways to transform. For those that are in math, you may have come across the Laplace transform. And the other one is a Fourier transform. Each of these have a benefit of capacity of what they can actually transform. One is that for Laplace, you're limited by time. Anything before time 0, you have to know an initial condition before a time 0 starts. And then you can use Laplace after that time. Fourier can actually do all time, but it is a little bit more complicated in the math portion of it. And so I like to always just use pretty much the Laplace transform and just know an initial condition to it. So we're not gonna get into the actual Laplace transforms and Fourier transforms. You're gonna do that in 3500. So what we're gonna do here is look at I take that back. I'll show you a simple way of doing the Laplace transform that we're gonna use, and then that we're only gonna just use one of them. So with the phasor is to describe the signal. Again, it's just the magnitude, and then if you have a phase shift, it's EJ to the phi or theta if you want to use theta for that. So if the book also uses another notation, the big angle notation, that means the same thing as EJ to whatever is in the angle value. So 10 EJ 53 degrees means the same thing as 10, and you say it angle 53 degrees. So these are the two terms that you're going to see. So let's see if I need to say anything more with this. Okay. 3, 2, okay. All right, so the properties, so important properties, I guess. Let's see. Like EJ, so J is referring to, like 1J means that there's no real portion. And so if I was to graph that, that means it has a magnitude of 1 on that imaginary axis. So J itself would be rectangular form. And then in polar form, it converts into EJ to the pi over 2, which remember pi over 2 is 180. And so 180 over pi, so that then becomes 90 degrees. So this would be your magnitude of 1, angle 90 degrees. So those are all the different ways of writing the same information. Rectangular form, and these two are polar form. A -1 is the same thing as writing EJ pi, which is 180 degrees, or EJ minus pi. So a -1 is going to be here. So this is 1J. And so this is, again, the rectangular form of it. And then these are your polar form. Those two, well, and this one will be, these three are going to be the most common. So a -J, so this would be a -1 is here. And then a -J is -1J. So again, rectangular form. And then these are the polar forms. There's anything else? So again, that big, this one, thing here, these are called the angle form of this. All right, questions on any of these? Okay, you have all the content you guys need for your next exam. So from here, a lot of practice is going to be a lot of practice. All right, so any requests on types of problems you guys want to make sure we do on Wednesday, or that I have available for you to watch on Wednesday?